sharing.
Okay, I can start sharing.
And
Is it okay?
yeah, sure.
Right.
Oh, very nice.
And I will start the recording.
Good.
Yes, it's good.
So first of all, I would like to thank the organizers for inviting me. And that is quite important because I'm just a beginner in quantum theory. And here we have so many great experts, and maybe I will get some feedback useful. And at the beginning, I would like to, of course, congratulate Nikita and learning with 60s. And I share my theory about the age, which some years ago, I went to a conference devoted to 60s of Yuji Kadama, a friend of mine. And the Japanese explained me that 60 is a very, very important age. That is 5 times by 12, the complete circle of life. And my theory is that until 60, you have to add years, and after 60, you have to subtract. And that's why people becomes, more childish when they get old. So now you just on the top and will subtract years and get younger and younger with every year. So my congratulations.
Thank you.
I would like to share another strange theory about quantization. And that is not a conventional way to do things. And I really will be happy to hear any feedback on that. So the plan is the following. I will first explain things which just fixed notation, what is quantum mechanics, what is classical mechanics, what the problem in quantizations I see, and then we discuss what is free associative mechanics, and why the title is quantization of dynamical system of free algebras. And then I will explain my definition of quantization and how to approach, and illustrate by some examples like Volterra chain, Toda system, Korteveg-de Vries system, and I will not be talking about non-abelian homogeneous quadratic systems because never time, let me do that. Right. Let's start from the quantum mechanics and classical mechanics. So what we have instead of phase space, I like to speak about functions on a phase space. So the functions, let's consider only polynomials to make things simple. So we have polynomials of commutative variables, and we have some Newton equation, for instance, with a first integral. First integral means constant of motion. We can introduce Poisson brackets in a standard way, write equation as a Hamiltonian equation, and any function of our dynamical of our variables P and Q which satisfy equation, we can differentiate in time using this Poisson bracket with this H with the Hamiltonian of the system. In a quantum counterpart, we have a non-commutative setup where P and Q are Hermitian operators. They have some commutation relations. I will explain this notation later. Well, that is basically we will consider some rational functions of parameter H, which is a Planck constant, and that is a free algebra, and this is a quotient of the ideal generated by the Heisenberg commutation relations. Equations are exactly the same. We have the same Hamiltonian, and the Hamiltonian is a constant of motion. If you differentiate this Hamiltonian using equation and using the commutation relations, you get 0. These variables not commute, they commute on IH, that is a Heisenberg, and can be written in the Heisenberg form. So that is a parallel things. So that's what I see, that ideal kind of quantization. So we replace functions of t and we replace by some Hermitian operators. Now, what the problems with quantization I see, or related problems. Usually people use so-called deformation quantization. So they just deform. That comes actually from not from Kontsevich. It comes from Dirac in 1925. He discussed that we need to kind of deform our rule of multiplication, becomes non-commutative, such that in the limit of Planck constant goes to 0, we get Poisson brackets. And then this theory becomes very popular, and people start to try to quantize the Poisson manifolds. So the manifolds equipped with Poisson brackets, such that in the limit you have some deformation constant, and in the limit you have Poisson brackets and some corrections. And there are several issues in this series which is difficult and require attention. One is associativity. So this multiplication must not only satisfy this property which is okay, but also should be associative. And that has to be taken into account of special attention. Another is a consistency of the algebra with the dynamical systems for finite h. If h is very small, we have Poisson brackets and everything is consistent, because we know classical mechanics is consistent with the Poisson structure. But and that issue was actually raised also by Dirac in 1925, that we have to be careful and show that for finite h, not in the limit, but for finite h, everything is consistent. Another important issue is the ordering of operators. So we have Hamiltonian, which depends on our dynamical variables or our operators. In commutative case, we don't care how we put these things, it's just polynomial. In non-commutative, everything depends how we arrange these operators, and the result may be different, and we have to be very careful with ordering of the operators. That is the issue, and that people always discuss, and it's not resolved up to now. Another thing which I was interested in and was thinking about is we know that many systems have multi-Hamiltonian structure. And when we're talking about deformation quantization, we say we quantize, we try to deform some Poisson manifold. Poisson manifold depends on Poisson structure, and we may have several Poisson structures. So which one we should deform? And that will be different quantization. Or we have compatible Poisson structures like Poisson pencil. So we can have, for instance, that is a Toda lattice example. We have Toda equation. Well, I don't like exponential. Let's write everything in polynomial variables. Very common way to write Toda lattice. So that is a Toda lattice in polynomial variables. It can be infinite or periodic. Does not matter, and it is known to be 3 Hamiltonian. I will write only 2 because 3 third is quite big, and I don't use it in my talk today, and there is a problem with it. So we have 2 Hamiltonian structures. One, I only present here non-zero Poisson brackets. So we have first Poisson structure with the first Poisson brackets, and that H2 is a Hamiltonian. If you just use this as a Hamiltonian Poisson brackets, you reproduce the Toda lattice. Or you can use another Hamiltonian, H1, which is actually the Casimir for the first bracket. And you can reproduce with a second bracket, and any linear combination of this bracket is also skew-symmetric and satisfy Jacobi identity. So that is also legitimate Poisson structure. So what we should deform, which one, and how this multi-Hamiltonian structure can be reflected in the quantum picture. That is another thing which I'm interested in. And the last question is, well, everything here kind of attached to the Hamiltonian structure, the Poisson structure. Can we define non-deformation quantization, which that non-deformation, that's nothing to deform. We don't have, any Hamiltonian structure. Is it possible to define this object, its sensible definition of these things? So basically, these issues I'm going to address today. Right. Now to do so, I first step, I go from classical mechanics or quantum mechanics. I want to some kind of super on top. It's not super in the super sense, but just the object which is above of everything. So-called free associative mechanics. So I don't want to consider commutative variables, and instead of commutative, I will consider free algebra. Well, here is example with 2 letters, but later on we go to many letters, infinite letters, etc. But to see this first example. So we have a free algebra, 2 letters, P and Q. You can, so there is no way to, there is no relations, no any way to swap these letters. So any words written as P, Q, Q, P, and in any order, they are all independent. So that is a free algebra. For simplicity over C. And dynamical system is nothing but a derivation of this free algebra. And derivation is it's a linear operation which satisfies the Leibniz rule. And we can write non-abelian Newton equation in on free algebra. Just to do the same. F is a polynomial. You can write this equation. We assume that P and Q are a function of T. So that is a good equation. If you don't like free algebra, you can think that P and Q are some matrices, n by n matrices, where n can be arbitrarily high, not fixed, or just square matrices. Or you can, because fixed, if you fix dimension, it's not a free algebra. You have Hamilton-Kelly theorem, for instance. And that we can ask questions, what any properties of equations of free algebra. Actually, I believe this equation should have some meaning, not only like intermediate step in my construction, but they should have some meaning. Maybe later on, they will have some meaning related to some maybe random matrices or some other meanings of probability. I don't know this meaning. At the moment, that is just intermediate step. Right. The first question, do we have any properties of these equations like we have for classical dynamical systems? Well, it has a first integral, for instance. Look, if you take P and Q commutator, PQ minus QP is element of our some element. If you differentiate in time and use linearity and Leibniz rule, you get 0. So that is a first integral of our system. But the Hamiltonian or standard first integral is not a constant of motion anymore. Well, if force is not linear. And that is example. So if you have this equation, actually this equation was shown on the talk by Victor Buchstaber in the first day, in the first talk. He shown this equation, and that is a Newton equation, example of Novikov equation for genus 1. So if you differentiate, use linearity and Leibniz rule, you will see that result is not 0, but can be expressed as a linear combination of commutators. And then people say that, okay, if it's matrices, we take trace, and then everything will be fine. And that's how they can find the real just first integrals in the matrix case. In the free algebra, we can introduce a linear space, which is a span of all commutators. It's not ideal, it's just a linear space, and consider the quotient of our algebra over the linear space over this linear space. And they say that, okay, we can define these first integrals as elements of this quotient space. And if the derivative, if the integral is not 0 in this quotient space, but its derivative is 0. And there are infinitely many first integrals for this equation, which is rather surprising, because in usual case we have just one, and every other is a just function. This equation has infinitely many symmetries. Symmetries means commuting flows, and that is non-abelian symmetries. There is a way to construct. There are infinitely many, and that is the properties of our equations on the free algebra. Right. Let's go quickly further. What's the difference between free algebra main difference and the commutative or quantum algebras? The size of growing is a very big difference, because what is the basis, additive basis in free algebra is any words, any sequence of P and Q with any powers we can write, and if this index is being different, it's a different words. And if we fix the degree of monomial, the number of monomials of fixed degree grow like 2 power n. If you have 3 letters, will be 3 power n, etc. So grow enormously. In the commutative case, the commutative algebra.
Sasha, sorry, why do you have on strictly non-negative indices I and j? Why are you sure that these are only polynomials?
Because that will be not a free algebra. Because we will have, yeah, I'm talking about free algebras. Later on, we can introduce negative. That is later. Let's talk very simple things. If you have negative, it's not free algebra, right? Because we have relation.
Right.
P multiplied by p minus 1 is 1. That is a relation. It's not free algebra. Right. Commutative case can be obtained from free algebra. We just take ideal generated by the commutator of p and q minus qp. And if you take a quotient over this ideal, the resulting algebra will be just commutative algebra, just the ring of polynomials of algebra of polynomials of commuting variables p and q. And quantum algebra, you take the same thing, but the quotient of the ideal generated by the Heisenberg relation. That's how we can get the quantum algebra. And in both these cases, the algebra admit the basis of normally ordered monomials. That means we can always put p in front of q, for instance, or vice versa if you wish, or while Weyl introduce some Weyl ordering, does not matter. So we can do, and the number of monomials of fixed degree growing linearly with n, not a power like. Moreover, any element can be represented. And in physics, people use so-called normal ordering. For instance, if we use these commutation relations, then we can normal order these monomials. If you normal order, you just represent in these bases. And if you substitute this normal ordering, if you normal order your result is this differentiation, normal order all monomials using commutation relation, you will get 0. That in quantum case, it is a first integral. It is a constant of motion. So that is what is the free algebra different from normal. Now it's a main slide where I try to explain my philosophy, which been published maybe about 2 years ago. Actually, this paper, when I sent it to archive, it was waiting about 2 years, 2 weeks to approve publication, because people were not sure that it is not a joke. Right. The first thing is a fact, mathematical fact, that any algebra, any associative algebra, can be realized or isomorphic to a quotient algebra of free algebra over appropriate two-sided ideal. So basically, we have any algebra. We can for any algebra we can identify it with a free algebra quotient over a two-sided ideal appropriate. So that is one-to-one thing. Now, what I mean by quantization, it is my definition. It's not common definition, so don't like it. That is, you have all rights to do it. So in my definition, quantization of a given dynamical system, I don't quantize any Poisson manifold or whatever. I am working with a dynamical system on a free algebra. So we have a derivation of free algebra. Derivation, that means we know how to differentiate all our generators of free algebra. So and we have linearity and Leibniz rule. That's it, nothing more. And then we search for two-sided ideals in this algebra, which are stable with respect to this derivation. That means if you take a derivative of the element of ideal, you get back to the ideal. And in this case, that is necessary and sufficient to be able to restrict our derivations on the quotient algebra. So then we can correctly define derivations of the quotient algebra. And the second property that I try to go from physics, from this normal ordering, etc., that the quotient algebra admits a basis of normally ordered monomials. So, like in commutative case, very close to commutative case. So there is no any appeal, any relations to the Poisson brackets or Hamiltonian structure, that pure algebraic consideration. These two, but surprisingly, you will see that the result will be the same as you do. Well, not exactly the same, but all cases quantization of standard Poisson, the deformation will be here, of course. Now, and by definition, this ideal which satisfies these two properties I call quantization ideal, and the corresponding quotient algebra is a quantum or quantized algebra, if you wish. Well, you can say that I deviate from the original problem, because originally people study the commutative case, and my starting point is a dynamical system on a free algebra, and that is a delicate step. So there are infinitely many ways to lift system from commutative to free algebra. You just can add to commutative. You can put variables in arbitrary order, or you can add to you can think that your variables not commute anymore, and you can add any element which is zero. I mean, which belongs to the ideal, means zero if your variables commute, and there are infinitely many ways to do so. But there is some guiding principle, because in physics or in our integrable world, we cherish some properties, like, for instance, symmetries. So we can, integrable equation have, for instance, the hierarchies of symmetries. So we want to lift our commutative equation to non-commutative to free algebra in a way such that this property preserved. So that makes this lifting basically unique. And that is kind of, well, it's not the answer, or because the whole idea is generic. It's nothing to do with integrability. But if you apply to integrable systems or to systems which have some symmetries, then you just pay attention to what you're doing. So if you lift, you can try to keep the properties which you value most, like, for instance, symmetries, or some, yes, Galileo or whatever, Lorentz symmetries, or symmetries, high symmetries, or other things you want to preserve lifting equation. Now, about ideals. Of course, I don't know the general answer about the ideals, what kind of ideals we can consider, but there is one class which I also work with a group of people, with Carpentier and Jinping Wang, and also with Buchstaber. So we just study some ideals, and this is ideals kind of very natural, I would say. So what we want, we start from algebra with n generators, free algebra. We let this algebra is equipped with some lexicographic ordering. So we say that xi is bigger than xj if I is bigger than j. That is just ordering. And also we can propagate this ordering, or define ordering of monomials. Basically, one monomial from xi and xj ordered if letter on the left is, if j on the left is bigger than, or I on the left is bigger than. So we have ordering in monomials, and then that is free algebra has this basis where any letters, any I, J, any any words here. And in this algebra, we define polynomials. The polynomials means any two letters we can swap. I will assume that our constants here, omega ij, not zero, so I don't want at the beginning some nilpotent elements. We can add them later. And when we swap, we can add some tail. And this tail, so that is by kind of, we start from that is a leading monomial, and all monomials here will be in our order less. So swapping, we reduce the order in the monomial. So if we have such ideal, then every monomials we can swap, and we can introduce the basis of normally ordered monomials. So that is a special ideals. This ideal has been studied. There is a dissertation of Viktor Lewandowski in Germany, that's Ukrainian mathematician, very good, well written, and he studied particularly these algebras, and he said that these algebras, the quotient algebra, admit Poincaré-Bergov with basis. It's like a basis of polynomials, for instance. You can add some other things, so consider further quotients. For instance, if you take xy, xj plus xy, xj, xy polynomials and xi square equals 0, you will get Grassmann algebra. So all these algebras, quantum algebras, Grassmann algebras, can be easily put in this framework. Now let's go to examples, because I don't want to. So I want to be really explicit to us. So let's consider the non-abelian Volterra system. Volterra system was that a chain Z is, so we have infinitely many equations. U depend on and they are on free algebra. Commutative case was known, I mean, since Zakharov, and then later Kass van Norbeke and Manakov show integrability. So Bogayevlensky, I think, show that in a non-abelian case is integrable. So there is a long story. I'm not going to talk about this story. So here variables stay in appropriate order. Look, it's this, you cannot change this order. If you put, for instance, un at one side, the system ceases to be integrable. So that show that this lift to non-abelian case preserve the hierarchy of integrable system. It has Lax pair, it has all structures, so that is a good lift of the. Actually, these equations are shift invariant, so if you just shift, you just change the index, and that is a difference algebra. So we can write one equation, and all others equation can be obtained from one. Now I want to play the same game. I just take an ideal, and the simplest possible ideal you can imagine, which satisfies the properties that you can swap two letters, is here. We write P, if you multiply P and Q variables, will be the same as a P and Q, but multiplied by some constant. We don't know this constant. And we know that is non-zero. And that is sufficient to reorder all monomials and put the biggest letter in front and lowest order at the back of a monomial. And of course, we will gain some power of omega reordering these monomials. So basically, these polynomials is a Gröbner basis in our algebra. Right. And then in my paper was announced result. Now the complete proof of all the result is in the preprint that you can see in archive with Carpentier and Wang. But that if we request this ideal is invariant with respect to dynamics, then you have restrictions that omega only the nearest variable commute on some constant, and if variable far from each other, they commute between each other. Well, this result in quantum world was known. It's not new. Ray, has a paper with this quantization. It was studied, you know, they studied Volkov, Fadeev, Takhtajan. Lots of people study quantum case, but they use quantum spectral transform and, you know, some big machinery to get this. Here, this result is basically a few lines of computations and proof. And that can be rigorously proved that if we have this ideal is invariant if and only if. I put here IH, well, because people like Planck constant. And if you want U to be Hermitian operator, then this alpha should be module equal 1. That is kind of obvious, because if you take Hermitian conjugation, should be, you know, should coincide, should be not a new equation. And this Volterra system can be written in the Heisenberg form, where Hamiltonian is just a sum of U. So that is the result. Actually, you can ask, we know that with a Volterra system, we have an infinite hierarchy of equations. And what we proved with Carpentier and Wang, and that is now a preprint, that the whole hierarchy of equations admit this quantization, that this commutation rule is compatible, or this ideal is compatible with all hierarchy. By the way, I forget to say that moving in this way, I mean, assuming that we get the ideal and we take a quotient, we guarantee that the resulting algebra and the multiplication rule will be associative, because we have associative algebra and we take quotient over the ideal. The result is always associative algebra. That is one thing. Secondly, we guarantee that all consequences of our equation, because we have a proper we induce proper derivation in the quotient algebra, all consequences of our dynamics will be consistent with this algebra with a finite h. So we kind of address all these two or three issues: ordering, consistency, and the right. And then this equation has higher symmetries. We have infinitely many higher symmetries, and that here is the next symmetry. And next symmetry also, as we have shown, that's a theorem that all symmetries can be written consistent with this quantization, and also can be written in the form of the Heisenberg equation. Here is Hamiltonian, so we can write infinitely many Hamiltonians explicitly. Actually, we can write infinite, and all this equation can be written in the Heisenberg form. So we don't use any quantum, any Lux pair, any quantum stuff, any R matrices, anything. It's just like that. Then interesting question about non-deformation quantization. That also was example in my paper, two-page paper in Russian Mathematical Survey. The question is, suppose we not start from the equation of Volterra, but from the first symmetry. That is the first symmetry of Volterra, and ask the same question: when the ideal, this ideal we start with, is invariant with respect to this equation, we know one answer, of course, that is quantization A, because that is when the it's the same as Volterra. But surprisingly, we find another answer, and another answer: this equation admits a different commutation relations, which are not deformation of any commutative case. So there is no any limit to any commutative case, and there is no any limit to the Grassmann case, because this minus 1 power n. So that is example of a non-deformation quantization. And what we proved it's not a fluke. We proved with in this preprint that you can find in archive, that every odd degree equation, here equation is odd degree. Look, you have u cube, and you have u5, u7, etc. Any odd degree equation from the Volterra hierarchy admits quantization 5. So there are infinitely many equations which admit quantization 5. And all even and odd admit quantization 4, and that is and that is quite remarkable algebra. I think this is a new one, and it's interesting to study it. I have not much time, but anyway, there are some ideals which are invariant but not allow us to swap all the elements, and that is a gray area. We don't know what that corresponds. So there is a way to restrict the Volterra system to a bigger algebra, not to the algebra with Poisson-Bergov basis, and that is example of the ideal. Interesting to look on the finite or periodical chains. For instance, with period 3, we can write chain with period 3. We can restrict all our symmetries on period 3, just count index modulo 3, and can ask the same question. But then, finite number of variables, we can afford to consider more general ideals. Like here, we have linear terms and the constant terms in the ideal, and the proposition is with a full proof in our preprint and announced in my paper that if period is 3, that the quantization is here, and where alpha, beta, and eta arbitrary constants is period is 4. We also have 3 constants, but we have such a quantization. And if period is 5 or bigger, that only this quantization survive and all other constants die because they not give us invariant ideals. If you take a system with so that here is a quantization with we'll address by quantum structure with period 3. So we have equation with period 3. We have 2 Hamiltonians, H1 and H2, and that is the classical case. We have 2 Hamiltonian structure. One Hamiltonian structure is so we have a pencil, mu and nu. So we have one mu when mu equals 0. That is one Hamiltonian structure, and we have another Hamiltonian structure when is mu 0 and nu is -1. So that is another Hamiltonian structure. That is 2 different Poisson brackets. And the same equation we can write with one Hamiltonian or when is another Hamiltonian. One Hamiltonian is a Casimir for one structure, another Hamiltonian is Casimir for another structure. And in quantum case, we have exactly the same picture. We have 2 algebras, 2 ideals, and we have 2 kind of commutation relations with one or another. So if eta equals 0, we have this commutation relation. If alpha is 1, we have this commutation relation. We have 2 Hamiltonians. They are central elements of the algebra, and the equation, the same equation can be written as in 2 different ways. It's exactly the same picture as in the classical case. So we kind of reproduce by quantum structure here. Okay. Well, for m equal 4, m equal 4, I want to show some appeal to some super integrability. We have 4 variables, we have 4 equations, and here is a non-deformation quantization. There is no any Poisson structure, anything, any limit to classic. But what we have 3 commuting Hamiltonians. We can build from these commuting Hamiltonians with these 2, we can commute 3 central elements of the algebra, and we have 1 equation. So we have 3 Hamiltonians, 3, and I think Nikolai will agree with me that that can be seen as a super integrable quantum system. We have 3 commuting Hamiltonians, and we have equation with the 4 on the 4 operators, etc. And well, I use one last minute. I will not talk about to show by quantum structure of Toda lattice. So if you have Toda lattice, you can play the same game. You can find the commutation relations depend on 2 deformation constants, eta and theta. If eta and theta 0, we have 2 directions. So we have 2-dimensional quantization of the Poisson brackets for Toda lattice. 2-dimensional quantization in 2 theta and eta. You can compute the conserved densities infinitely many, and you can reproduce the classical by Hamiltonian structure for Toda and the corresponding quantum commutation relations for which one-to-one correspondence you can see, and in the limit you will reproduce from the left the right, and you will see this chain of equations that H1 is the Casimir for theta quantization, or I forget theta here, and the equations, the same equation can be written in one quantization or another quantization. It's the same, exactly the same dynamics, but the quantization are different, and what the quantum theory behind representation and all the machinery which need to be developed further is not here done. It's just a kind of basic level of the theory. And the last thing I will say is that we discovered that the Toda system, even sub-hierarchy of Toda system, admit non-deformation quantization. Non-deformation quantization. Well, I stop here because my time is over.
Well, thank you. Maybe questions and comments?
Саша, так сказать, ну вот эта алгебра, как бы, там, то есть, как бы, если так про квантовую механику думать, то вроде там где-то должно быть пространство состояний или просто состояние на этой алгебре.
So to get, first of all, you need to have a representation of the algebra, right?
Да, вот я как раз про это и хотел
In the
сказать.
Hilbert space. No, that is, I just try to stay on a basic level to define the sensible and consistent commutation relations, which make sense and which are rigorously, I mean, from the mathematical point of view. And then you should make a representation of your operators in some Hilbert space, and you can do it, in like here I even take care about that operators, all operators are Hermitian. And then having these operators, you should study, the spectrum of these operators, etc., and develop further the quantum mechanics. No, I don't say that I solve all the problems. I just try to make one step in a non-conventional way, in a way which, first of all, allow us to build non-deformation quantization, and secondly, not appeal to any structures like Lax operators, etc. Actually, that is a very important issue and very important problem that we are always thinking, but not yet find a way how to relate this to Lax operators, to R matrix, etc., to the whole machinery developed, during these decades. And for instance, if you quantize this pencil, your R matrix should kind of depend on two deformation parameters, two Planck constants, H and A and theta. No, that is the next stage of the theory. It is not developed, and I hope if you recognize that it is something, you will go in this way.
Very, very interesting. I mean, it's one more question. So it reminds me the following, that you can have deformation families of Poisson structures, and then you can do deformation quantization of these families of Poisson structures, and then you should have families of associative algebras.
Yeah, these algebras are that is exactly the answer to your question, because what we have, look, in this case, when I start with maybe I think I start.
I mean, Sasha, these algebras, associative algebras, they are not deformation quantization of a pencil.
Yes, it is. This algebra 7 is a deformation quantization of a pencil. Mm-hmm. In pencil, we have two constants. We have two structures, structure like this structure and the second structure, right? You can construct linear combination of these two structures. Mm-hmm. To every you have this. To every structure, you have your own quantization. But you can consider pencil, and for pencil, you will get quantization 7.
Oh, very interesting.
Yeah, and but what I want to really draw your attention that there is a non-deformation quantization which not correspond to any pencil, but you still can write Heisenberg equations. I mean, exactly in the same form. For Toda or for Volterra system, you can write this equation, and they are not correspond to quantization, to deformation quantization of any pencil. And algebra is associative, non-commutative, associative, and in the case of Volterra equation, for instance, here, that is an algebra. You have 4 letters. Look, that is all commutation relations between algebras. You can see that it is not commutative. I mean, does not have any commutative limit because we have minus here. It does not have limit to Grassmann because we have plus alpha and minus alpha, but you have your Heisenberg equation. And algebra is associative, nice. I mean, the Poisson algebra over the ideal generated by these relations. You have 3 commuting Hamiltonians. Everything is fine. So Hamiltonian actually H square, you should take H not commute, it's H anti-commute in this algebra. You have H square, H1, and H2. 3 commuting first independent operators, algebraically independent. You can write your Heisenberg equation and you have 4 degrees of freedom. I mean, that's what I want to draw your attention.
Okay.
Anyone else?
Can I ask a question?
Sure.
Sasha, it's Volodya Rubtsov. Sasha, what did you find when you studied this non-commutative? I mean, not quantum in sense of deformation, but just non-commutative systems, which are similar to Lotka-Volterra systems. Did you find some analogies with, I would say, non-commutative, fully non-commutative Penlevé equations? Because, you know, we have found with Retek 10 years ago, maybe 12 years ago, fully non-commutative Penlevé-2 equation in a skew field, in associative algebra, which looks like a kind of fraction field.
Yeah.
With special derivation. And then we tried to do it for Penlevé-4. But for Penlevé-4, it is not possible to find a unique non-commutative analog. If you think that Penlevé time is also non-commutative. Recently, with Retek and with young collaborators, with Ira Bobrova in particular, and with Gosha Sharygin, we have found analog of non-commutative, fully non-commutative P4, but it is not a unique equation, it is a system. And this system, for some values of parameters, are very, very similar. It is not the same, but very close to non-commutative Lotka-Volterra. Maybe you can have some hint.
Right. I discussed this issue with Sokolov, Volodya, and
it is Volodya always consider matrix non-commutative.
but his matrix is not essential. You can put to free algebra. He does not use that as a matrix. You can write on the free algebra. You know, free algebra is better because not everything can be realized in finite matrices. Finite dimensional. For instance, the Heisenberg algebra cannot be done in finite dimensional matrices, right? But free algebra is better in this sense because it gives you lots of freedom, and it works. But the only thing you need to do, the things it works. Well, it is not finished. We discussed this. We had some progress, but you know, let's stop at some stage, and everybody does own things. What you need to do, you need to introduce non-commutative constants, not only dynamical variables u, which depends on time, or you know, operators, but also non-commutative constants element of algebras whose derivative is 0, but they not commute with each other, and then your ideal, which will also involve this constant. So when you quantize, you have to find the, or I mean, quantize, by quantize, I mean, you find the commutation relations, you should also give commutation relation between this constant and the letters U in your chain. So it works. You can find things. It looks like it works, but it is not finished. But that, I think, is a good way to proceed.
It's very interesting. I know this idea to use non-commutative constant, but in the same time, they always try to keep time commutative. Yeah, it means.
Well, that I think related with Leibniz rule, how you can be consistent with the Leibniz rule. That's a problem, I think.
Well, you can make a choice of left or right, and then trying to keep it. Anyway, it is possible for Pinlever 2 and for Pinlever 4. It is also possible if you agree to consider Pinlever 4 as a system of second-order non-commutative expressions.
Oh well, what I want to say that if you see that this, if you think that this approach is sensible, I mean not like a joke, then probably we can join our efforts and go this way, because I think a potential in this way, because that resolve a few things like associativity. You have associativity by default. You have consistency with the system by default. You know, you can control the ordering of operators because you want to keep some structures like hierarchies and you know, some other properties like your favorite Pinlever property, etc. So you have some guiding and then it should work. So you know, like miracle happen in all this time, all the time in the case of integrable systems.
Yeah. Okay, thank you.
Can I ask one stupid question? What is the relation to the quantum Hamiltonian reduction of your construction?
This construction is not appeal to any Hamiltonian structure. Apparently, we get the same results, apparently. But when we start, well, if you have Hamiltonian structure, if you know Poisson brackets, then you have a good idea how to write ansatz, or how to start, what kind of ideal you should start with, because otherwise ideal is so huge number of parameters and very difficult to work, very difficult to control. If you have already known Hamiltonian structure, then you have a very, very good idea what the structure of your ideal. And then it's the computations become short, and then you can, compute all these things, the commutation relations, which is not obvious at all. Even if you know the commutation relations, I mean the Poisson brackets, to compute the commutation relations, it's a problem and can be not an easy problem. And here it gives you a very good guidance how to do it. Yeah, and well, here there is a slide about multi-Hamiltonian structure of stationary KdV or Novikov equations. Very, very, it's a quantum. It's very, very similar to classical. So it's not appeal to any Hamiltonian structure, but apparently it appears when it's possible to find. But in non-deformation quantization, there are non-deformation exist, and there are examples here. We cannot relate to any Hamiltonian structure because there is no any limit to commutative or Grassmann case.
So I mean, this is some kind of a theorem that on your example, no additional Poisson structure can be introduced, right? Or it's just a hint that there are no such.
Well, I will show you. I will show you. Let's consider finite dimensional case. That is a finite dimensional case. look, there is no any limit to commutative case or anti-commutative case. In anti-commutative case, you can say, okay, probably we can, I mean, the Grassmann case, we know that there is a Hamiltonian structure in the Grassmann case. Or it may happen that, like we have a commutative case, we have a standard Poisson structure. In Grassmann case, we also have Poisson structure, don't we? And here is a case which is neither commutative nor Grassmann, but probably maybe there exists one, but nobody knows. You know, that is a new structure, new algebra, nobody study, and at least I don't know any answer, anything. What I know, I have algebra, I have Casimir operators, I have everything consistent. Algebra is associative, dynamics is consistent, everything, you know, is fine, but I cannot relate to this algebra any Poisson structure. Because
Okay. Thank you.
But you also, Sasha, cannot define any shift of indices for this algebra.
Yes. If you yes, let's go to the to this theorem here. Here, it's a quantization B. Look here,
Yeah.
shift should be equal to 2. The S square, the shift square is everything algebra. I mean, if you have infinitely many variables, then everything invariant with respect to shift square, the standard square. And so basically you can split system on even and odd variables, you know, even and odd size, and then will be shift. But this algebra, this quantization or whatever, you know, ideal is not shift invariant, but invariant with respect to shift square.
Yeah.
Did I answer your question?
Okay, yes, this. Okay.
Right.